All right, let's talk about those tricky string problems. You know the ones where you have to balance multiple characters. If you've ever hit a wall with one of those in a coding interview, you know exactly how tough they can be. Well, today, we're going to break down a really powerful, repeatable pattern to solve them in Python. No more guesswork, no brute forcing, just one elegant solution.
So here's the core question we're tackling. How can you efficiently find every single substring where the characters A, B, and C show up the exact same number of times? Now, your gut instinct might be to just, throw a bunch of nested loops at it and check every single possibility. But that's going to be way too slow. We need a much smarter approach.
Okay, first things first, let's make sure we're all on the same page. What even is a balanced substring? It's just a piece of a string where our target characters, in this case A, B, and C, have identical counts. So if you look at the string abccbaabc, the little chunk ABC is balanced, right? One of each. But hey, so is abccba. That one has two of each. Our job is to find all of them.
And that really gets to the heart of the challenge. Like we said, brute forcing it, checking every single substring and counting characters every time, it technically works, but it's just so inefficient. If you want to nail this in an interview, you've got to be faster.
Which brings us to the secret sauce. This is the core idea, the little trick that makes this whole problem just crumble. It's all about a clever shift in how you look at it so you're not tracking a bunch of useless information.
So, your first instinct is probably what mine was. Just keep a running total of the A's, the B's, and the C's, right? It seems totally logical. But here's the thing. The secret to a really efficient solution is realizing those absolute counts, they don't actually matter. No, what matters is tracking the differences between them. And that right there, that's the aha moment. Instead of the counts themselves, we only care about the gaps, the differences between them. This one idea simplifies everything, and it's the absolute key to this whole pattern.
So how do we actually do that? Well, we turn it into a neat little package. We pick one character to be our baseline, let's just use A, and then we create a state. This state is just a tuple, a pair of numbers, that tracks the differences. It's always the count of B minus the count of A, and the count of C minus the count of A. And here's the real magic. If we see the exact same state at two different spots in the string, that's a guarantee. It means the substring between those 2 points has to be perfectly balanced. It's like a signal.
Okay, that's a cool idea, but how do we actually build it? Well, to make this work, we need a way to remember every state we've already seen, and just as important, where we saw it. And the perfect tool for that job? You guessed it, a hash map, or as we call it in Python, a dictionary.
And this is what makes this whole approach so incredibly powerful. It's not just a one-trick pony. This single pattern, calculate a state, store it in a hash map, can solve at least 3 different but related problems. If you want to count the balanced substrings, you just store how many times you've seen each state. If you want to find the longest one, you only store the very first index where you saw a state. And if you want to print all of them, you store a list of every single index where that state popped up. Same core logic, different results.
Yeah, this quote really nails it. Notice how the same prefix state logic solves 3 different goals depending only on what we store in the hash map. The core engine, that state calculation, it never changes. All you're doing is tweaking what you decide to save in your dictionary, and boom, you get a completely different answer. It's just so flexible.
Okay, theory is great, but let's be real. Seeing this thing in action is where it's all gonna click. The best way to build that intuition is to just walk through an example, step by step. So let's do a trace of the algorithm. All right, here's the complete Python code for printing all the balanced substrings. You can see how we start everything off. We initialize our counts to 0, and we create our prefix map. Notice we give it a starting state of 0, 0 at an imaginary index of -1. That's a crucial little detail. Then we just loop through the string, update the counts, calculate the new state, and check our map. So let's trace this.
Okay, we're at the very beginning. Index 0, the character is A. Simple enough, count A goes up to 1. So what's our state? It's 0-1, 0-1, which gives us -1, -1. We check our map. Have we seen this state before? Nope, it's brand new. So we just add it to our map, saying, hey, we saw state -1, -1 at index 0. Nothing found yet, so we move on.
Next up, index 1, we hit a B. So now count B is 1. Our states calculation becomes 1 minus 1, 0 minus 1, which simplifies to 0, -1. We look in our map again. Is 0, -1 in there? Nope, another new state. So we just add it to the map. Still, no balanced substrings have been found.
And here we go. This is the magic moment. At index 2, we see a C. Now all our counts are 1. Count A is 1, count B is 1, and count C is 1. So the state is 1 minus 1, 1 minus 1, which is 0, 0. Now, we check our map. Have we seen 0, 0 before? And yes, we have. Remember that initial state we put in at index minus 1? That's our match. This is the payoff. It means the substring between that old index, minus 1, and our current index, 2, is balanced. And what is that substring? It's ABC. We found our first one.
Okay, that was a pretty detailed walkthrough. So let's step back and boil this all down into a few key takeaways. The goal here is to give you a simple, powerful mental model that you can carry into any interview. First, a few important ground rules, or caveats. You have to use the relative differences. If you try to use the absolute counts as your state, this whole pattern just breaks. Also, keep in mind this works beautifully for a small, fixed number of characters. If someone asked you to do this for the entire alphabet, you'd probably need to adapt the strategy a bit. So here's the mental model I want you to walk away with. Just think of each prefix state you calculate as a checkpoint on a journey through the string. Anytime you hit a checkpoint that you've already visited, ding, 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 that's your signal. You've just completed a balanced journey between those 2 points. And what you do at that checkpoint, whether you just count it, save the location, or add it to a list, that's totally determined by what the original question was asking for.
So now that you've got this pattern in your toolkit, here's a little challenge for you. How would you change this to handle 4 characters? Let's say A, B, C, and D. What would your state tuple look like then? Give it some thought, because once you really get this pattern, you realize you can solve a whole class of these problems.